Hi, ladies and gentlemen. I'm very happy to be invited to present in this conference today to present my work, which is about the complete semantics of LLVM. Um, First, let's talk about what is LLVM. It's written in C++. I think it acts as an intermediate languages, programming languages that a lot of high-level languages are supposed to compile to it, and it can also compile to a lot of low-level architects. Um, so I think the key point of the LVM is that this SSA formed. It has a nice structure that a lot of compiler optimizations are easy to be defined and analyzed on these programming languages. And now the question is that why we need to care about the semantics of it? Because firstly, it is widely used, and the LLVM documentation has more than 219 pages, and it contains a lot of operations, intrinsic functions, and library functions. So it's huge. And previous work has identified a lot of bugs in the LLVM compiler, which is Clang. And I think the most important issue is here is that for a lot of this kind of imperative languages, there is a gap between the formal specification of them and the real implementation of it. So on one side, people try to use a mathematical formula to define the semantics, while on the other side, in the real world implementations, a lot of tricky things that cannot be defined mathematically. So in the semantics of LLVM, we actually tend to minimize the gap, try to define the LLVM IR semantics as close as related to its real-world implementation, which is Clang. So let's talk about some utilities and features about the KLLVM. Firstly, let's talk about some utilities. I think one of the utilities is that we have two versions of the KLVM. One of them is defined in K, the other one is in Isabelle. On the K version, it can automatically generate an interpreter. And by using the interpreter, we can see the trace behaviors of a program, especially a multi-threaded programs. And in the LLVM version, we can also utilize the LLVM version to prove properties about a specific code program under a concurrency environment, including the single-threaded concurrency behavior and multi-threaded one. And by the Isabelle version, we can also try to define a compiler optimization and show that the compiler optimization is correct with respect to all the programs that are allowed in KLLVM. For the features, I think we define the complete set of LLVM IR instructions. We also support some intrinsic functions and library functions. And then more specifically, we actually define the KLVM as an abstract machine that executes a LLVM program. The abstract machine is closely related to the real implementation of a computer that executes LLVM IR programs, and it can be divided into two conceptual parts. The first one is the execution model that basically to simulate the single-threaded concurrent behavior, and it allows out-of-order and speculative executions to execute a single-threaded program. And also we have the memory model to talk about the inter-thread concurrency, where the whole memory model is being proved to respect the C++ memory model. Here is the structure of the KLVM. On top of that is a LLVM IR program in its concrete format. And then by the static semantic steps, it can be passed into a front-end AST format. And through some static analysis, it can be passed again to a back-end AST format. And then the dynamic semantics is defined in terms of the backend AST format. The dynamic semantics of a KLLVM is an interaction between three different things. One is the execution model, main model, and a single instruction level dynamic semantics. So let's talk about these few things one by one. For the static semantics is basically a simulation of the different static analysis phases defined in Clang. Firstly, you will pass a IR program into a front-end AST format, and then we will try to get some global information, such as the module information, and also try to analyze those information. And we also will do some checks and process the global pointers and static memory locations, etc. And then we will actually type for each of the functions defined in the program, we will type check those functions. Especially, we will also have a validity checks on the bodies of those functions, such as checking the SSA format and checking other validity checks. And finally, we will actually translate the front-end ST to a back-end ST format and hand for the dynamic semantics for execution. For the dynamic semantics, basically it simulate how an application machine can execute a possibly multi-threaded LLVM IR program. We actually created an actual machine, like I have already mentioned. And then the nice feature about this actual machine is that it's divided into two parts. One part take care of the single-threaded concurrency behavior. The other part take care about the inter-threads concurrency behavior. So let's talk about each of these individual parts one by one. Let's first examine what is the execution model. The execution model basically connects the single instruction level dynamic semantics with respect to the whole thread CPU framework. The CPU here means that a conceptual device to execute one single threaded instruction at a time. And then the CPU framework actually allows out of order and speculative executions, which stands for the single threaded level concurrency behaviors. We also, but besides that, the execution model has more on top of it because LLVM is such a complicated languages. It also contains some threading libraries and then mutex libraries, and all those things need a global device to provide information for each individual threads, and those things are defined in the execution model. So let's look at the structure of an execution model. Here is the structure of the execution model. On the left-hand side, on the top of that is the global control unit, which is the global device. Provided the information for each of the threads for the prefix and then mutex libraries. For example, when a thread is creating a new thread, you will basically go to the thread status to get some information about the global counter for the new thread ID, and also place a block in the thread status device and say that, okay, there is a new thread here. And then the wait John threads is basically a device used for providing the mutex information between two different threads. For each of these threads in the thread pool on the left side here, each of the thread has the formulation of the right hand side here. Is actually a complicated structures. Each of these different devices is actually a mathematical entity defined in K and Isabelle, and then the interaction of them actually forms the formulation of the execution models. Let's first discuss the to execute cell. The to execute, like I said, all these programs have been processed into a backend ST format, which is essentially a list of basic blocks. And then the to execute cell will actually store the list of basic blocks, which represents the program. And then the to execute cell will select one of the block and then to place place all its instructions one by one to the instruction queue. And then the instruction queue will first to discover whether or not an instruction has a dependency on top of it based on the information provided by the DDG device here. The DDG device is basically providing the information about the dependency relation between different instructions in the program. And then once it discovers that one of the instructions has no dependence on top of it, then if the CPU cell is empty, you will send that instruction to the CPU cell for execution. The CPU cell is a central device to actually execute one instruction at a time. When you execute an instruction, it depends on the different type of instruction you will try to interact with the different devices. For example, if the instruction is an arithmetic instruction, then it will calculate the result and then store the result to the registers. If the instruction is a function call or a stack memory allocation instruction, then we will try to interact with the stack and finish the job. If the instruction is a write and read instruction, memory instruction, then you will send a request, memory request, to the to commit cell in the local memory device here. And then the local memory device will try to interact with the main memory on the right, and then got the feedback from the main memory if the request is a read. Now let's talk about the memory model. The memory model basically talk about defines the inter-level mode concurrency behaviors. So it has need to finish few jobs. First, for those local memory devices, then we talk about in each of these threads. You will try to commit or send the memory operations or memory requests each one by one to one of the memory cache, and then the memory cache will actually try to commit all one of these and collect all these memory requests from different threads, and then commit one of the memory requests one by one at a time. And also you will change some of these local information inside the thread accordingly. Besides that, because we assume that we have a multi-memory caches, then we need to talk about the consensus across all these memory caches. All these behaviors combined together actually is the memory model, and we show that this memory model is sound with respect to the C++ memory model. So let's find an interesting diagram about this memory model. On the left-hand side is a set of threads as seen in this execution model. But each of these threads only has only its local memory device can talk to the memory cache. And in the lifetime of one of the threads, it can only talk to specifically one memory cache. But different memory cache can talk to many different threads at a time. So the idea is that once a memory request or memory operation is in the to commit cell, the to commit cell will send a memory operation to the mem_op list in the memory cache. The formulation of the memory cache is on the right, as shown here. And then in the memory op list in the memory cache is you will receive different memory requests from different threads one by one, and then you will also try to execute one of this memory operation at a time to the bimap, which is basically the representation of the heap. It's a map from the a memory location to a byte. But besides that, for a chunk of memory bytes or for a chunk of memory locations in the bimap, you will also have extra information stored as an object in the object port in the memory cache. The idea is like this. If a program has a malloc allocation, then the malloc will, when the memory is execute the malloc operation, you will actually create an object in the object port that provides an extra information for a chunk of memory location in the bimap. And then This byte is useful to provide extra information, such as a range size information for the memory trunk. It's also useful for detecting memory race behaviors. For example, if two different threads try to write at the same time, for example, if one of the threads try to have a non-atomic write, which is split into several different small atomic writes and stored in the memory of ellipse, and during the time execute all these non-atomic operation for one of these operation from a thread, and another atomic or non-atomic operation from different threads happens, then in this case, race behavior happens, and then the information stored in the complete and race cell in the object cell will detect this race behavior and send a feedback to the thread, and specific tells that there is a race happens. So this is the formation for each of this memory cache, but we have many different caches. So that we need to talk about the consensus of the different caches. The consensus is actually very simple. We assume there is a leader cache, and then every time when memory operation is about to be committed to the heap, one of the memory cache will send the message to the leader cache, and then the leader cache will send a feedback telling the cache that it is about to commit the memory uplist, depends on the consensus information. Here is the talk for today. Thanks for listening. Thank you.